Hi, my name is Magdalena Schüttler. I am studying and working at the Center for Computational and Theoretical Biology at the University of Würzburg, and I will be talking a little bit about our project. We are interested in finding and quantifying imaging-based biomarkers for Fabry disease, and in this case, we are specifically interested in left ventricular hypertrophy and papillary muscle hypertrophy, which are both cardiac markers. Fabry disease is a very rare disease. Its prevalence is estimated to be somewhere between 1 in 170,000 to 1 in 40,000, and it's caused by the mutation of the GLA gene, which encodes for the enzyme alpha-galactosidase A, which is responsible for the degradation of a group of molecules called glycosphingolipids. So you can imagine that if this enzyme is mutated in a way that reduces its enzymatic activity, these glycosphingolipids cannot be degraded anymore, and so they accumulate basically everywhere in the body. Fabry disease presents itself with highly variable and non-specific symptoms affecting a range of different organs, including but not limited to the heart. And this variability and non-specificness of these symptoms often entails delayed diagnosis, misdiagnosis, and thus delayed initiation of treatment or ineffective treatment. We are trying to improve this clinical situation by characterizing left ventricular hypertrophy and papillary muscle hypertrophy as imaging-based biomarkers for Fabry disease because they're both thought to be potential biomarkers. For that, we are developing a fully automated image processing pipeline that can quantify cardiac metrics from three-dimensional short axis-signed CMR scans. So for our analysis, we have data from two different sources. We have access to the UK Biobank dataset, from which we have identified 18 Fabry disease patients with irrelevant cardiac imaging. And in addition to this, we have access to longitudinal CMR data of 28 Fabry disease patients that was acquired by our collaborators at the FACIT, which is the Fabry Center of the local university hospital. Our pipeline is coded in Python. It's open source and platform independent, so everyone can use it if you want to. It's linked at the very end of the presentation and also in the poster in the QR code. In brief, our pipeline segments the blood pool, which is this inner cavity of the left ventricle. This allows us to define the end diastole, where the left ventricular myocardium is the most dilated. And in this diastolic time point, we are measuring the left ventricular hypertrophy metrics using the UKBB cardiac module, which is a pre-existing deep learning-based segmentation tool. And we're quantifying the papillary muscle hypertrophy markers mostly using traditional image processing methods. Left ventricular hypertrophy is the thickening of this, let me show you, of this left ventricular myocardium. It is typically considered to be a late marker in Fabry disease, but still used clinically for diagnosis because the diagnosis of Fabry disease is often so delayed. So first of all, we are comparing the Fabry disease left ventricular hypertrophy metrics with a cardiac healthy control. And as you can see, there's definitely a considerable difference between them. Depending on how you try to correct it, it may or may not be significant. I would say it's kind of around the edge of significance. If we look at the ROC analyses, we can definitely confirm the diagnostic value that's already known of left ventricular hypertrophy with AUC values of just under 0.7. This means there are definitely some diagnostic value there, but it's definitely not useful as a standalone marker, and we are also not expecting this for a rare and complex disease such as Fabry disease. So this is, I would say, still a very positive result. Moving on to the papillary muscle hypertrophy metrics, we did not find any evidence for them being useful in diagnosis, but we have found that one of the metrics, the PMLE ratio, is significantly increasing with age in the Fabry disease group, but not in the cardiac healthy control group. And so this indicates that there might be some prognostic relevance. We are still analyzing this currently, so we're definitely working on painting a clearer picture of what this exactly means and how this might be potentially used clinically. I'm not going to go into this very much, but basically we see that the image processing pipeline and the metrics themselves are pretty stable over a 3-year follow-up, which is which is definitely good for the robustness of our pipeline. So to sum it up, we have developed a fully automated pipeline for the image processing of these metrics in Python. Our pipeline is free and open source, so everyone can use it. If you want to look at it, you can do it in this QR code. Yeah, with that, I'd like to thank you for your time. If you have any questions, feel free to meet me on Tuesday during my poster session or message me. My email is right here, and it's also linked in the QR code. So I'll do my best to answer as soon as possible through the emails. Thank you.